We are going to move into our final presentation of the day. It is a presentation with the principal scientist at RheoSense. Before I introduce our last speaker, I do want to remind you, we encourage you to follow us on LinkedIn, Twitter, and Facebook. It is the ideal way to stay up to date on all of the latest rheology and viscosity news and updates. If you have any questions throughout the presentation, please ask them in the questions panel or in the chat panel from the webinar pane, and we will answer those questions at the end of the presentation, but you can ask them along the way. No need to hold off until the end. And now, without further ado, I am pleased to introduce our final speaker of the day, Dr. Stacy Elliott. She is the principal scientist at RheoSense. Dr. Elliott earned her PhD in chemical engineering from Princeton University, where she studied the effects of soluble polymers on the structure and rheology of colloidal suspensions. She's obtained her extensive experience in rheological knowledge through her education at Carnegie Mellon University and Princeton, as well as her experience at both Alcon and DuPont. Today, Dr. Elliott will be talking about probing particle aggregation with shear rate and temperature-dependent viscosity measurements. And without further ado, it is my pleasure to introduce and pass it over to Dr. Stacy Elliott. And Stacy, just so you know, I can see your screen, but you are still muted.
Oh, okay. Can you hear me now?
Yes.
Okay. I think there's a little confusion there. All right. Sorry for the delay, and thank you for the very nice introduction. And let me get started then. Let me get into present mode. Okay. So as Eden had said, I'm going to be talking about trying to understand aggregated structures by using shear rate sweeps or shear rate dependent viscosity. I did intend to include some discussion on temperature, but I think in the interest of time, we'll just stick with the shear rate dependence. And so the purpose of this topic really is that, as many of you know, at RheoSense, we're very narrowly focused on viscosity measurements. And so internally in our work, we often don't have the opportunity to complete complementary techniques such as particle sizing, like you heard about this morning from Sham Shear at Kraft Heinz. So we like to really try to take full advantage of our viscosity measurements and try to extract as much information out of them as we possibly can. And so that's really, the basis of this discussion is how can we really fully utilize our measurements. And this is a common problem of interest to many of our customers, particularly in the pharmaceutical industry. So let's go ahead and get started. So I'm not going to go in a full viscosity review and discuss this because I think, we do this in pretty much all of our discussions that we give here at RheoSense, but I did just want to remind everyone the idea behind the shear flow environment and what that means. So introduction of a shear flow, this means that we're creating a flow field where we have a velocity gradient that's perpendicular to the direction of flow. So this shearing motion, meaning that the adjacent fluid elements are moving past each other at a different velocity. In other words, they're sliding past each other. If you think about this type of deformation, then I think it becomes clear why the steady shear viscosity is so sensitive to what is happening at the molecular level. And really, it gives a reflection of how the components, in the case of today's discussion, we're talking about particles and more specifically protein molecules, how these interact, and then how these interactions will then influence the microstructure or spatial arrangement of the molecules in the solution. So with that in mind, before we get into the data, I also wanted to sort of, with the structure properly relationship in mind, introduce why viscosity can be a very useful tool in the formulation development process. And particularly, I'm talking about particle systems, and I'm going to include protein molecules as a type of particle, albeit soft, and with some different features than particles in the strict sense. But and that's actually what our data will be on later with model systems. So if you think about working in the formulation development of particles or proteins or antibodies, oftentimes you're trying to modify the formulation to control how these components are interacting. And so in the case of proteins, which are inherently attractive, one tends to add different types of excipients, such as the individual amino acids that I have shown here on the top of the page, to try to control those interactions, those attractions, and prevent the formation of large-scale aggregates or clusters, which can lead to a variety of problems for application reasons. So the idea is we're adding these excipients to the formulation with the intent of modifying the interactions of these proteins or particles. In the case of the proteins, we're trying to minimize the formation of these larger length scale aggregates, which is really what we mean when we talk about the microstructure. The interactions, the attractive interactions of the proteins, which we can modify with the introduction of our excipients, are going to be the driving force in addition to concentration for the microstructure that exists. And as I said, with the proteins, it's going to be aggregated to some extent. Question is, can we control it and minimize that? So knowing then that the viscosity measurement is very sensitive and reflects what's happening in this microscopic realm, we can sort of monitor how successful we were in our formulation by looking at the viscosity for the different formulations that we have. And not just a single point viscosity, and not even just say a plateau viscosity, but really the viscosity, the whole entire curve, viscosity as a function of shear rate. Because we're going to want to look at some different transition features, such as this critical shear rate where we see the onset of thinning. And so you can imagine that if you monitor what you're changing in the formulation with the viscosity, you can sort of cycle around here until you get something that's useful to you for your product. Okay, so the main system that we're going to look at today is a commonly used protein, bovine gamma globulin, and we're going to introduce also some typical excipients that would be added to control the inherent attractive nature of these and modify the viscosity with the assumption that we're modifying the extent of cluster or aggregate formation. So we have a control buffer here, a common buffer used in the pharmaceutical industry. And we're going to introduce some of these individual amino acid excipients, histidine and arginine in two forms, with and without HCl. And then we've also sort of included in the analysis imidazole and guanidine, which is basically these end groups that are found on each of the individual amino acids. And all of our formulations are going to be at high concentrations, so therapeutic levels of the protein. And so what we can see then, off the bat, is that this low shear plateau viscosity, so the Newtonian region at lower shear rates, is modified by the presence of these excipients. So we can see that the addition of all of them does in fact reduce the viscosity from the control formulation, but to varying extents. In some cases, we're seeing nearly a 50% drop in the case of the L-arginine. So obviously, because all of these formulations have the same level of protein, and introducing these additional small molecules at modest levels at 125 millimolar, the presence of these alone is not going to lead to this change in viscosity. So it is reasonable to think that we are, in fact, adjusting the interactions and therefore adjusting the microstructure, specifically minimizing the formation of these clusters. But the purpose of today's talk then is to say, okay, can we look beyond just this plateau viscosity? Let's look at the entire curve and see if we can do some analysis that's going to suggest that that concept is indeed correct, or hypothesis is correct. So let's first take a look at the viscosity versus shear rate curves for the gamma globulin with the different excipients. So we can see viscosity as a function of shear rate. And just as we noticed on the previous plot, that we have the low shear plateau, the Newtonian region before the onset of shear thinning, is highest for the control group, excuse me, but then decreases as we add the different excipients. What's not necessarily obvious in this plot, but I think will be as we start going through the analysis process, is that in addition to this change in overall magnitude of the flow curve, we're seeing a shift in the onset of shear thinning as we change the level of excipient. And that's one of the things that we're going to strive to use to our advantage. Okay, so we're going to, for the type of analysis that we're going to do here, we're going to borrow some concepts from colloidal science. So we're going to view these proteins as a colloid, as a particle, as I alluded to at the beginning of the talk. And we're going to use what's done in the colloidal systems as basically a framework for our interpretation. So proteins certainly fall into the colloidal size domain, which is about 1 nanometer to 1 micron. And this size domain has, the bounds exist for 2 reasons. So the upper bound at something close to a micron is there so that these objects or particles or proteins are small enough such that Brownian motion is still relevant. Hence the little video that I have here. So we're talking about things that are small enough that the thermal fluctuations in the solvent basically creates continuous motion. And the reason that this is relevant here is that this Brownian motion is going to act as what I like to think of as a restoring mechanism. So when we're introducing this external flow field, which is acting to disrupt the equilibrium state, the Brownian motion, the existence of the Brownian motion is going to act to restore that. And although, because we do have an externally applied flow field, when it's successful, so the external flow field does introduce some minor deviations from equilibrium in the low shear plateau, because this mechanism is acting to try to bring it back towards equilibrium. And so the presence of this Brownian motion, this restoring mechanism, then generates what's referred to as a thermodynamic stress to distinguish it from hydrodynamic stresses. And this is what then is going to impact the magnitude and range of the viscosity curve. So it's going to impact the magnitude of the low shear plateau, and then it's also going to impact what is the range of that plateau and where is the onset or the critical shear rate where thinning starts to occur. So, and then the other bound, which is the lower bound here, it's about a nanometer, is that these objects need to be larger than the solvent molecules, which we want to view as a continuum in comparison to these larger objects, particles or proteins. And so generally when dealing with colloidal theory, we treat the system as what we say is a pseudo one component system. So we have the protein or the particle in this continuum. And we don't really worry about, say, when we start adding these excipients, these different individual amino acids, we don't really worry about how they are specifically interacting with each other and even the protein molecules. We just want to consider how is that going to impact the interaction potential between these proteins or particles. In other words, how do all these components that I put in there, how do they impact the pair interaction between particles or proteins as they come together in the fluid? So just to be a little more clear, in the case of our protein situation, what we think happens when we do introduce these different type of excipients to these inherently attractive proteins. So our plot here is basically what I've referred to as the interaction potential as a function of separation of our, model. A model view of the protein is basically occupying some sort of spherical volume. So the interaction potential, if you're not familiar with that particular function, and perhaps it might help to understand that the negative of the derivative of this potential is just the force between the objects. And so what that means is that positive values of the potential in this region here are basically what we refer to as repulsions. And so these act to stabilize the proteins, because this repulsive barrier is going to prevent it from moving into what we refer to then as the attractive region, where we have a basically stickiness to these, which can lead to the aggregation. So the idea when we're trying to adjust the excipients to adjust our interaction is, we're either trying to sort of minimize, if possible, this attraction, which is going to lead to aggregates, or if, perhaps another option would be to maximize this stabilizing barrier so that we have some sort of kinetic or time stability, keeping us closer to a dispersion of primary units as much as possible, or for as long as possible. So that's sort of the idea of the formulation variations, is that we're going to alter this interaction in some manner, which is going to influence our microstructure. And our goal is to move away from this sort of aggregated state towards something more dispersed. And as we move into the discussion of the analysis, I want to have everyone thinking about the structure, and more specifically these aggregates that we inherently have in the protein systems, because these aggregates, because they have different length scales, are going to diffuse with different time scales. So larger objects will move more slowly, smaller objects will move more quickly. Okay, so still a little bit more to prep before we actually start analyzing the data. I wanted to talk then in sort of a qualitative interpretation of the shear rate profiles based on everything that I just sort of outlined from the sort of colloidal view of these types of formulations. And so we're looking again at a viscosity as a function of shear rate, where we have oops, I jumped ahead there, sorry. My animation got ahead of me. So we do have a low shear plateau, as we discussed, and then this critical point where we see the onset of shear thinning. And then, although we can't quite access it with our particular instruments, there would be then theoretically a high shear Newtonian plateau if we went to high enough rates. So then let's think about, why do we even have this low shear plateau, and what does it mean, and then what does it mean relative to the onset of thinning, the onset of non-Newtonian behavior. So as I mentioned, if we're reviewing these with the colloidal framework, where we have this Brownian motion that's existing due to these thermal fluctuations in the solvent, then this is a mechanism that's acting to restore the equilibrium state, despite the fact that we have an external flow field applied. So in this region, we are perturbing it, but only slightly, and it's an only slight perturbation because of this restoring mechanism, or the Brownian motion. And this motion in resistance to the flow is generating this elevated thermodynamic stress. So this is why we have this higher low shear Newtonian plateau. However, at some point, as we are ramping up the shear rate, we're intensifying that external perturbation. And so at some point, we're going to overcome this Brownian motion so that it can no longer try to keep the structure near its equilibrium state. And so this is when we see the onset of the shear thinning at this critical point. And then as we ramp up the shear rates and make this external force stronger and stronger, eventually we're going to sort of wipe out all of these thermodynamic forces. The stresses in this high shear plateau are purely hydrodynamic, and we're very far from an equilibrium structure. So with that in mind, I wanted to go over this so that we could start so that there's some sort of rationale for the way I'm going to do all of the scaling, which is, our analysis. So with that in mind, to decide how are we going to scale our viscosity, what we're going to do then is we want to look at, again, I'm sorry, I'm using my laptop with the pad here, so I keep jumping ahead. We want to look at this basically degradation of the thermodynamic stress as we ramp up the shear rate. And so what is the magnitude of the thermodynamic stress relative to the hydrodynamic? That's the viscosity minus the two plateaus, the difference in the two plateaus. So the difference in this plateau and this plateau are really the magnitude of the thermodynamic forces and the type of structure that's been generated. So that's what we want to monitor, is we monitor the loss of that thermodynamic behavior or thermodynamic contribution to the stress here. So we're going to subtract off the hydrodynamics and then scale it on this total thermodynamic contribution. However, since we don't have this high shear plateau, we're going to need to modify this slightly, and we'll just use the solvent viscosity. So what we're going to look at is we're going to look at in the decay of this of the contribution of the thermodynamic stresses to the viscosity. That's the rationale behind the scaling. Okay, so now we want to scale the final part of the analysis would be to scale our shear rate. We're trying to non-dimensionalize everything. And we're going to do that by changing the shear rate to the Peckley number. So why are we doing that? So let's just first start with sort of a qualitative view of what happens when we change shear rate. So just like in the previous talk where they were talking about changing the frequency and how that is related to different time scales, the shear rate is also, changing the shear rate also will probe the occurrence of different time scale events. So because its shear rate is inverse time. So what you can think of is that the lower shear rates, this means that we're looking at larger time scales, and at the higher shear rates, we're looking at shorter or smaller time scales. And so if you think about that, as we talked about the structure and the different size scales that can exist in an aggregated formulation, when we're at these higher rates, we're really probing more the smaller objects, and as we move lower and lower shear rates, we're probing the larger objects. And so the first thing we can see then is that in comparison to the control formulation, which shear thins about here, as we add these different types of excipients, we're shifting the onset of thinning to a higher and higher rate, sort of qualitatively implying that we are in fact successfully breaking down these clusters into smaller objects with the introduction of the excipients. Okay, let's see if we can do something then that will suggest that in what I would say a semi-quantitative way. Okay, so now, we've already talked about shear rate representing an inverse time scale. So, and we've talked about diffusion, which is basically the, how long does it take for these objects to move about under the thermal fluctuations. So let's then think about non-dimensionalizing the shear rate by looking at different time scales that are governing these events. So it's pretty straightforward to determine the characteristic time scale of our external flow. That would just be the inverse of the shear rate. And remember, this external flow is acting to perturb the structure. And then, so what then is the time scale that we want to associate with our Brownian motion, which is acting to restore this equilibrium structure. So our Brownian time scale is going to be given by the square of the radius of a cluster divided by the short time self-diffusion coefficient. And this just comes from rearranging the expression for the mean free path of an object as it diffuses a distance on the order of its size. So that's basically where that comes from. We're looking at how long is it going to take for this object, this cluster, to diffuse a distance about equal to its size. My apologies again. So now we've introduced then the length scale of these objects. So we need to come up with how are we going to represent the short time self-diffusion of these objects. So what we're going to do is basically an modified Stokes-Einstein form of the diffusion, which is kT over the viscosity times the length scale with a factor of 6 pi. And instead of the primary proteins, we're going to use the cluster size, which we're using L to characterize. And because we're in the concentrated system, so remember we're up at 250 mg per mil of the protein, so quite concentrated. So as sort of a way of including the fact that that will also hinder the motion and slow down the motion, rather than using the solvent viscosity, we're going to use the low shear plateau viscosity. So sort of in what would be an effective medium type approximation. So we have this cluster sort of diffusing around in the solution as a whole. So these are our two time scales: Brownian motion acting to restore structure, shear flow acting to disrupt. So now this Peclet number, and it's a modified Peclet number because the true Peclet number would be using the Stokes-Einstein relationship. So it is slightly modified. Is going to be a ratio of these two characteristic time scales, the Brownian relative to the shear. And so with all of the information, we can get an expression for this, and we can see that this gives us now a dimensionless shear rate. So the Peclet number is a dimensionless shear rate. And so now how are we going to use this scaling to understand something about the aggregates or clusters in our system? So if you think about what's happening down here on the plateau, as I mentioned, the Brownian motion is sufficient to minimize the perturbation to the external flow. So the particles or clusters are moving much more rapidly than the characteristic time scale of the flow field. So down in this plateau region, the further we go down in this direction, the lower and lower the Peclet number. And so then as we start ramping up the shear rate, we're basically going to start increasing that Peclet number till at some point, there's going to be a balance with these two time scales. So somewhere in the vicinity of a Peclet number of 1, we start seeing that transition from the Brownian motion being significant to the shear flow, transitioning to the shear flow becoming more significant in being able to disrupt the structure. So what we're going to do is we're going to do this scaling for our curves, and we're going to extract a characteristic length scale of these clusters by saying, I want this transition or the onset of shear thinning to occur at a Peclet number equal to 1. Okay, so now we have the fully scaled curve. So we have the scaled viscosity as a function of this Peclet number that I just mentioned. And things collapse nicely, so this is very encouraging. So now we have the scaled viscosity, where we're looking at basically the decay of the thermodynamic contribution to the stress. And then the Peclet number, where we're looking for that transition from the importance of the Brownian motion to the basically external flow, wiping that out. And what we can see then here on our table, if we look at the different formulations where we have the control that has no excipients, and then we have the various individual amino acids and functional groups included as the excipient. And this is listed so that we have the highest viscosity at the top, and then we gradually go down to lower viscosity with the excipients. What we're seeing is that this cluster size or characteristic length scale of our cluster does in fact drop proportional to viscosity. So as viscosity goes down, we're seeing this cluster size go down, and the extent that it goes down depends on the excipient. So there is an exception to this where we have one of the guanidine in the HCl, where it's sort of an outlier, it doesn't follow the trend that the others do. I'm not sure if there's something to this, or if perhaps it's just that the data here was a little noisier in the vicinity of the onset. So perhaps it's a data issue, or perhaps it is, an outlier for a more physical reason. But in general, what we're seeing is that this analysis is supporting the idea that these clusters or aggregates, the presence of them with the larger size due to the sort of uncontrolled attractions, does lead to a higher viscosity. So it's these reversible aggregates leading to higher viscosities in these types of protein solutions. So just to show you that it's not just that particular group of experiments where we see a similar type of behavior, where we introduce those individual amino acid excipients. We've also done this analysis where we've prepared, again, a 250 mg per mil gamma globulin solution, where in this case, instead of the amino acid excipients, we've varied the type of salt and the level of salt that was in the buffer that we formulated these in. So the rationale behind the different behavior with the different salts is that if you're familiar with proteins, adding the salt initially generally will increase solubility. So this is called the salting in phase. But then as you add more and more of the salt, it starts to, what they say, salt out. And the theory behind this is that at some point you have these salts which have a pretty strong affinity to water. And the thought is that these salts, as you have higher and higher levels, will start pulling water away from the protein, so dehydrating the proteins in a sense, which can lead to further aggregation or reduced solubility of the proteins in solution. And the extent of the influence that each salt has on this effect, this salting in, salting out, really has to do with the affinity of water for the salts. So the level of hydration each salt molecule or ion would have. So that's just sort of a background of why this would change the viscosity of the protein solution so much. So what we have here then, again, same scaling, doing the same process where we're trying to shift this Peclet number to be 1, and therefore that's how we extract our characteristic length scale for our cluster. Again, we see that we have this collapsing into a master curve. And here, I have it like shifted backwards. So I have the highest viscosity down below, and then as we move up, we see decreasing viscosity. And again, because we have a more dramatic shift in viscosity, we're seeing a larger shift in our characteristic length scale of the cluster. But again, we see the same idea. In the system where we think we have the most aggregation and the most, which leads to the highest viscosity, we're seeing a larger cluster size or aggregate size. Again, suggesting, giving merit to the idea that it is these reversible clusters that do form and lead to the enhanced viscosity in the protein solutions. So finally, to kind of pull those two data sets together, a common way of looking at this in the context of dispersions or even semi-dilute polymer solutions where the polymers have yet to become entangled is sort of look at the magnitude of the plateau viscosity as a function of what would L cubed. So this would be essentially the effective volume occupied by one of our aggregates or our clusters. And you can see a power law relationship with either our experiments where we did salt type and ionic strength, or in the case where we did the amino acid excipients. And we have a consistent sort of power law with each group of experiments, although there is some sort of shift. And this type of trend is also consistent with what was seen in the reference that I gave down below here, where they were doing this on some actual concentrated monoclonal antibody formulations. And they sort of backed up this rationale with some complementary neutron scattering. So in terms of why our two groups of data don't overlay perfectly, I think, I can only, guess, but my guess would be that we used 2 different lots of gamma globulin for these different experiments. And if anyone's familiar with gamma globulin is a mix of 2 components, which can vary slightly from lot to lot. And then the other factor that I think could be relevant is that you can have the gamma globulin molecules existing in these reversible type clusters, which I've been talking about, which we can control by changing the environment. But then they also have a certain level of irreversibly bound dimers, which you can't separate those due to site-specific interactions that are quite strong. You can't separate those no matter how you adjust the formulation. And so again, that could be the exact quantity of those could vary depending on the different lots. So I think, perhaps a mixture of the two components that exist in the gamma globulin and then the level of what is referred to as the irreversible bound dimers as opposed to these reversible clusters that form. So I want to sort of stop there and thank everyone for joining us today. And, just point out that, as I mentioned, our focus here is viscosity. And so, this type of work that we do specifically here is really geared towards trying to extract the maximum amount of information that we can from the viscosity measurements that we can do. And of course, if you have access to complementary tools, then all the better. But this is our perspective. So thanks for joining me, and I'll let Eden see if there are any questions.
Thank you so much, Stacy. We do actually already have a question that's come in. So I'm going to go ahead and start addressing those. If anyone else has questions, please drop them in that questions panel, and we will take the remainder of the presentation time to answer those. So, Stacy, the first question is, did you encounter zero or negative viscosity at any points in your measurements? What were the deductions for these scenarios, if any?
I did not see any of those during our experiments. So there was, so I can't comment on how I would deal with it because we didn't see that.
And do you have any viscosity temperature plots to show? They would like to see how they conform with Arrhenius's law.
So I don't have any in this specific presentation, but we do have experience where we do the temperature dependence of the protein solutions. And so long as we don't get to the point where we're inducing denaturation, sorry, I can't talk today. As long as we're not denaturing the protein, so below that transition temperature, we do see Arrhenius type behavior, and the activation energy will depend on the protein, the concentration, and the types of excipients that are in the formulation. And it turns out that we see higher activation energies for the proteins that we think are more aggregated or have these larger clusters. The rationale behind that, based on some literature, is that higher activation energy is indicative of sort of hindered, motion of these aggregates in the solution. So hopefully that answered the question.
Are there any differences between the salty fluid and the unsalted fluids to see the effect of salinity on the fluid rheology at various concentrations?
So I'm not sure, do you mean, could you read that again? I'm sorry.
Oh, of course. Any differences between the salty fluid and unsalted fluids to see the effects of salinity on the fluid rheology at various concentrations?
So in reality, although some of those fluids, I added, extra levels of the different types of salt. In reality, all of our buffers have some level of salt, and we have characterized those individually to see how, the background viscosity varies with the different type of salt and the different level of salt. So I'm not sure if that's what you meant. So I don't have any of those background viscosities or the buffer viscosities present, but we've certainly looked into those.
We will wait just a few minutes to see if any other questions come in. And of course, there are a couple coming in. So this one's a little longer, Stacy. So I'll read the whole thing, and if you need me to repeat, let me know.
Okay.
Can you speak to how viscosity measurements can be used along with DLS measurements to assess composite nanoparticle systems, such as polymer-coated metal or metal oxide nanoparticles? And there's a second part of the question, but do you want to address that one first?
So am I correct in summarizing they want to know how we can use viscosity in combination with DLS to characterize particles in general?
Yes, and specifically it sounds like nanoparticle systems.
Nanoparticle systems. Well, certainly, if you have the ability to look at, DLS, then you can use that in combination with the experiments that I was just discussing to sort of gauge whether or not the types of length scales that you're extracting from your data are reasonable. And then, given DLS is generally done on dilute systems, whereas these types of experiments that I'm talking about have to be done on concentrated systems, then that might start to clarify whether or not the same level of aggregation exists in the concentrated state as it does in the dilute state, because that's always a little bit of a question mark there. Does dilution change the level of aggregation or cluster formation that you have? So I guess that's my first thought there.
And then the second part of the question is the viscosity light scattering method for the determination of the core size of polymer-coated nanoparticles the only method for characterizing, or are there other methods that you know of?
It's the only one that's coming to my mind. I mean, I guess you could do it. I guess the only other way that you might be able to do the polymer-coated nanoparticles is still a light scattering technique. It would be static light scattering, though, because in that case, you'd have essentially like a core shell type structure. And so you could try to fit there are theories for the form factor that exist for that core shell structure. So in that case, you could use potentially static light scattering alone and those models for core shell type structures. But those, off the top of my head, unless I'm forgetting something, which I might be, those are the only ways I've ever kind of dealt with that.
Someone's wondering, did any of your formulations exhibit Herschel-Buckley fluid behavior?
No. Not this group.
And then just a question I'm going to address really quickly. Stacy, someone's asking about a video of the presentation. Recordings of all of our presentations from today will be sent to our attendees from today's event. And as far as the presentation slides, for the speakers who do wish to include them, they'll be included with the recording. And for speakers who only wish to share the recording, the slides won't be included in a downloadable format. But for Stacy's, please correct me if I'm wrong, I believe we will be sharing her slides along with the presentation.
Yes, we can certainly share them.
And we'll wait just one more minute to see if any more questions trickle in, because I know as soon as I start to conclude and thank you, they will. All right. Well, thank you so much to Dr. Elliott. Oh, nope. See, of course, as soon as I say that, someone asked, can I ask the geometry of your rheometers?
Sure. So I didn't include a discussion of our products. I wanted to focus on the data, but our method is a rectangular slit method. So it's a microfluidic technique where we're basically controlling the flow rate through a microfluidic channel and monitoring the pressure drop across the channel, which is how we then calculate the viscosity. And just to be a little more specific then, all of the data I collected was either on a flow channel with a 20 micron or a 50 micron channel depth. So this is very different than the rotational instruments that some of our other speakers have discussed.
Well, I don't see any more trickling in, so I want to say thank you so much, Stacy, for such a wonderful presentation and for concluding our event today. This was wonderful. And thank you to everyone who attended the 2022 Virtual Viscosity Summit. We hope that you enjoyed the day as much as we did. And just one last reminder, the recordings from all of today's presentations will be sent out at the conclusion of the event, so be on the lookout for those. And one more time, if you do have any questions or want to connect with anyone on our team, we do encourage you to. And I will go ahead and put up our handles one more time. So please feel free to follow us on LinkedIn or Facebook or Twitter. We will share rheology and viscosity news and updates there. We want to thank you all again for joining the 2022 Virtual Viscosity Summit, and we hope you all enjoy the remainder of your afternoon or evening.